Okay, yeah, so I'm excited to give this talk. This is a subject that I'm personally interested in my spare time. I don't do this AI stuff for a living, and I'm just learning, so that's the disclaimer. So if I make any mistakes, people that catch it, please, shout out. So let's just get into this. I work at Cognitect. I work remotely, so I do Clojure every day, which is really cool. And Twitter handle is GigaSquid. And if anybody's wondering, my handle came back or was from the AOL days, back in the AOL days. And I would play like Half-Life during lunch with my office mates on our LAN in the computer. And I registered for a name. I tried to register for Squid, and Squid was taken. And I was like, oh. And then I was like, Mega Squid. Mega Squid was taken. So that's the Giga Squid. So I finally ended up as Giga Squid. This talk is about artificial intelligence. And this is a really hot topic nowadays, of course, because there's been some really exciting things going on. Earlier this year, Google's AlphaGo beat humans and let us win one game, which I thought was very nice and smart of it. Other things that are happening, self-driving cars. I'm really excited for self-driving cars, especially since my son is 13 and I have 3 years. I'm really hoping that the technology will just push really closely and I won't have to deal with all that. We also even have AI dreaming and being creative, which I find really fascinating. And with like the pace of artificial intelligence and all the technological pace of everything going on, it makes you kind of wonder, where is this all going? Could this be a threat to us? And some people don't like what he says, Elon Musk, but he says, maybe we're risking summoning a demon, and we should have some oversight in what we're doing. And actually big companies like Google and Facebook, they're actually getting together and starting to talk about how we can use this power responsibly, because it's like Spider-Man, right? You have this power, you've got to be responsible with it. But a lot of people are worried about AI, and some people take into their fears, and when you talk about artificial intelligence, like to your family or my mom and dad, they think, Terminator. You're trying to build Terminator and Skynet, right? This is really scary. But that's really not what we have today. I mean, if you look at a reality check of where we are with artificial intelligence and like robots today, it's really more like this, right? Robots falling down is always funny. But did anybody watch this? This was from the DARPA 2015 finals. Yeah, it was pretty awesome in a very strange way. So I was watching it with my daughter, and the point of the competition was it was supposed to be humanitarian, like rescue robots. So they're putting them through a course of getting in Jeeps and going into buildings, opening doors and turning valves. But they try to make it more realistic, so they gave them really crappy Wi-Fi to work with. So the programmers were in this little base, trying to control the robots, and they did it at an incredibly slow rate. So you'd be watching this robot try to open a door, and it would take like 5 minutes for his hand to get out there, and then finally he'd turn it and then fall down. It was so. We're not quite there yet. And humans, I think we are still pretty cool, and I hope that we continue to be cool for a long time to come. And if you look at humans, I mean, just simple things that babies do are really still hard for a computer to do. And we're still struggling with that. Face recognition is one thing. And again, we've made great strides with face recognition using convolutional neural networks and things, but it's still, I mean, our babies can do it. Same thing with talking, recognizing words and speech. You know, there's a whole field of study trying to get computers to have chatbots that can talk to us normally and understand what we're saying, and it's still a challenge. So let's take a step back and think about what is talking. Well, you know, there's letters in our representation of talking. Those letters make sounds, and together these like sounds that I'm making as I'm talking to you are linguistically called utterances. But of course, there's a meaning behind those sounds, right? For example, when I say, "What is your name?" you actually know that I want a piece of information from you, and that's important. And this meaning can actually be rolled up into kind of like higher level categories. And these higher level linguistic categories are called speech acts. This is a picture of a book who came up with the speech acts, John Searle. And it goes into the philosophy of language. And in it, there are speech act categories. There are statements, kind of familiar to us people that work with computer programming. So an example of a speech act statement would be, "My name is Karen. I'm stating a fact." Of course, there are speech act questions. You know, what is the airspeed velocity of an unladen swallow? All right. I was waiting for that. And then there are these things called expressives. And they're an interesting category. They're, you know, thank you, you're welcome, or LOL. They expose the internal state of the speaker. So it's, you know, however you want to think about that in programming. Oops. So today we're going to kind of use these concepts, and we're going to try to make our own mini chatbot. And we're going to learn some things along the way. And, you know, maybe we'll be able to use this on the internet, who knows? Because on the internet, nobody knows that you're a read eval print loop, right? So our mission is, if somebody's typing at a keyboard and we get some text, we're just going to try to determine what broad speech act it is. We want to determine if it's a question, a statement, or an expressive. And there's the kicker. We don't want to count on punctuation at all. Because I know when I'm like in a chat room and I'm typing stuff, I forget to put the question mark all the time, right? So we want to be able to kind of categorize the text without the question mark. So what tools are we going to use to do this? Well, the first we're going to use is Clojure. Has anybody here used Clojure? Woo! All right. So why are we going to use Clojure? Well, I really like it, number one. So that's what I like to use. But other reasons of why I like it are that it's simple, it's elegant, it's expressive, and it's powerful. I'm just going to give just real brief, this isn't a Clojure talk or anything, but I'm just going to give you some real brief background for those of you that haven't seen it, what it is. So it's a dynamic language. It's also a functional language. It's got Java interop. It runs on the JVM, and it handles concurrency. And we're just going to dive in real quickly into each of those categories. So it is dynamic. So unlike Java, if I want to define a cat, I don't need to say what type it is. I simply say, hey, this string is a cat. Oh, and I know at this point you're like, oh my gosh, what about all these parens? So The parens are kind of scary when you first see it, but I promise you, like when you start getting into the language and you have a good editor that does like the matching and everything, they just kind of disappear. And then people actually think of them as hugs for your code. So don't let the parens scare you away. So it's a functional language. Functions are first-class citizens. And in Clojure, here's just quick how to define a function. Use the defin. So this is defining a function, say hello, that takes a parameter of a name. And it's simply going to concatenate hello with the name and return back a string. So in the bottom, you see an example of it being called, just in the parens. Say hello, puppy is going to return hello, puppy. Clojure also has Java interop, which is really convenient because the JVM and Java has tons of libraries to use, and the JVM is really powerful. So if you actually look at the class of a string, it's really just a Java-lang string underneath. And you can call its methods on it wrapper-free. So I'm calling to uppercase on that string and getting the uppercase. So it makes a lot of things very easy. Clojure also has great concurrency support, which is a lot of the reason why people use the language. It's built on immutable data structures, and I'm not going to go into what these things are, but I'll just mention it has these things called vars, refs, agents, atoms, and this library called core async that all make this stuff possible. Also, and this is, I think, is a really cool feature lately that needs some more attention, is Clojure has Clojure script. So you can do almost the exact same things that you do on the browser on the server, and you can share the code between the two with these things called CLC files. So that's really cool. Right, so we've gone over our tool Clojure, but back to our problem of wanting to do something with text. We need something to parse, right? When you type in some text, we need something to parse it and give us some information about it. We need some information about the text that they put in to help determine its meaning so we can categorize it as a statement, question, or expressive. And we're going to use some help for this. We're going to use Stanford's core NLP library. This is, as far as I know, it's the state-of-the-art parsing library for natural language English. So what exactly are we going to be doing with this library? If we have some text, like I like cheese, which I do a lot, it's going to break up these things into tokens, and then it's going to annotate them. And it's going to annotate them with these things called POS annotations. And if you all remember your grammar, which I don't, you'll be reminded of what actually this is with an abbreviation. And the code for these abbreviations can be found in this big list of part-of-speech tags in the Penn Tree Bank project. So you can see down there, like number 12 is a noun singular, or 13 is a noun plural. So there's a lot more below that you can't see on the screen. So in the end, what we want to do is we want to have a function that we can call that will process some text of our I love cheese, and then give us back some sort of data structure that's going to encode or have these part-of-speech tags. So what you see below is this is a vector in Clojure, the square brackets. And then there are maps within the square brackets. So it's a vector, so it's a list of 3 token maps with a token I, and then it's part-of-speech tag and for each of them. So the last one is cheese with the part-of-speech noun. So yeah, so this is when we get to switch over, and actually I'll show you some code real quick. So we're going to be looking at a Clojure project. Can everybody see that? More or less? Do you want me to bump it a little bit? I would if I knew how. Does anybody know how to turn that light off? Is there? That's up.
There we go.
Okay. So can everybody see that now? Okay. So what I'm showing you now is kind of the project file. And this is just showing you that I'm pulling in the libraries for Stanford Core NLP. And there's an extra one for the models. All right. And this is kind of scrolling off here because of the resolution. And I'm not going to talk through all the code, but I just wanted to show you a little bit. This is doing a lot of Java interop, but it's pulling in all the Stanford Core NLP classes. And there's different properties that you can set of what you want to parse a text. You can have tokenizers, you can split on sentences, part of speech, lemmas. So lemma is, it just gives you one representation for if you like, I ran, I run, it just gives you one representation for all those. There's even sentiment analysis in there, which is kind of interesting. So I just have some functions here that are turning the text into data and getting those tags. And then there's actually some code that sets up some chain references that if you have multiple sentences, and we'll see some examples of this, it tries to link like a name with he, if you said David went to the store. So, and there's the process text function. So the main point is I kind of wanted to show what this tags looks like. So if I process text and say I like cheese, bump the font on this, you end up with some token data, and the sentiment is neutral on it. Here's the lemma, like, here's a part of speech, and even give some animacy, which I don't really understand. But if you're in linguistics, I guess it makes more sense. So here's another example. How about like a double sentence? David loves cheese. He went to the store. Oops. I can't type. Okay, so this is a little bit longer because we're having different sentences. Let me make this full screen here. So you have the sentence number, you have David. It even recognizes that David is a person, which is interesting. Loves has a positive sentiment. And then if we actually go down to the refs, you'll see where it's trying to chain up the refs. So you have from the first sentence, David is actually linked with the second sentence, he. You can be stronger in your dislike of cheese. And we can see what that looks like. Sentiment very negative. And then, of course, you could do things like, I love Cincinnati, which you all should. And it actually recognizes that Cincinnati is a location, which is nice. So the library is doing quite a bit for you. All right. So yay, we have data. We can take something that somebody types in our REPL, and we can parse it out into some different tags and get some information about it. That's really cool. Now we can do some machine learning, right? Well, we're going to do this, and we are going to use Weka. It's a collection of machine learning algorithms. Have anybody seen Weka before? All right, so we got a couple people. So this is a really powerful tool. The neat thing about it is it lets you explore and try out different models, because there's different ways that you can use machine learning. You could use neural networks, you should use decision trees, you can use tons of different methods, and you can experiment and see which one works best for your data set. And there's also a Java API, so you can use in your Java program, and for me, like, I can use in my Clojure program, which is really nice. But wait, we don't have enough data to machine learn. You need like something to teach the machine learning program to train on. So we're going to need some examples of statements, questions, and expressives to have any hope of doing this at all. So I thought about this problem very hard and found this site called answers.com. And thought, hey, I could maybe use this for my corpus. I could scrape it. Look, there's all these. The thing that I liked about it is that it was just regular people putting in random stuff, and it didn't seem to be curated in any way. So there was bad grammar and you know, just silly things. But it seemed like it would be the level of messiness that a chatbot might need to be trained on. So I was just going to scrape this website and then have, you know, each blue bit here be a question, and of course I can strip off the punctuation of it. And then each bit below can be an answer, but I'm just going to use the first sentence of it because I really didn't want to get in the whole multi-sentence thing. So I wrote a quick Clojure scraper just to gather some questions and answers together, and I wasn't, you know, going for any sort of rigor because this is just a fun project that I was doing. And I wasn't going for any mass quantities because I wanted to have something small enough that I could manage and explore with. I definitely wasn't going for, you know, the hundreds of thousands of examples that you'd normally see with machine learning data sets. But you know what the fun thing is? You really don't need that just to get started and explore, and it makes it a little bit more manageable as you're doing it. So here are some examples of the questions, like what is a floater exe? I don't even know. Is bottled water or tap water better for your dog? That is very important. And many more. And 200 statements that went along with that question. So yes, it depends on the quality of your tap water. That's really the answer for you. So yeah, so I have questions and I have answers now for my data set corpus, but what about expressives? Where am I going to get information for that? Well, I had no idea. So I just made up a list of about, I don't know, 40 of them of myself. So including things like great, thanks, you're welcome, IDK, which I actually learned from my kids. What's up, you know, that sort of thing. So let's take a step back now and kind of think about what we have. We have data for statements, we have data for questions, we have data for expressives, and we have a way to parse them and get that part of speech data from them. And we can turn that into features for our machine learning. So what are features? Features are just encoding of data that we are going to train our computer to use for machine learning. Which leads you to the question, of course, well, how do you choose the right ones? We have all this data that you saw that in the parsing. How do we choose which ones are important or which ones are not important for classification? And yeah, that's actually not an easy thing to do. And you will find in research, people devote their lives to, you know, studying aspects of this problem. But you know, we are lucky that we can stand on the shoulders of giants, and we can look at other people's work and research and use it. So my secret weapon a lot of time is Google Scholar. If I have a problem, I start looking up papers and see what other people have done about it. In particular, I found this really cool paper that was classifying sentences as speech acts in message board posts, which was really pretty close of what I wanted to do. And what they said in their paper, for their features, They chose sentence length, the number of nouns in the sentence, and this one was interesting. If the sentence ends in a noun or an adjective, if the sentence begins in a verb, and this one is pretty self-explanatory, but the count of the WH part of speech tags. So those would include like the who, the what, the where, the why. So that kind of made sense. So what we're going to do is we're going to create Weka input files, and we're going to do that by taking each one of those examples and transforming them into features in this thing called an ARFF file format. So the ARFF file format for Weka kind of looks like you have this metadata tagging at the top here. You've got, it kind of tells you what features are in there. It's got the sentence length, which is a number, the number of nouns, whether it ends in a noun, begins in a verb, the WH number, and then at the end, the type, which it's going to say is either going to be an assertion, a question, or an expressive. And then below, under the data tag, you have all your data. So that's the file format that we're going to create with our corpus. Right. So I'm just going to show you what that ARFF file looks like real quick. Ooh. So here's what our file looked like, and it's got a bunch of questions, a bunch of assertions, and down here it has our expressions, and they're all our features. So we're going to fire up Weka, it's over here, and to tell you the truth, I've only used this first button on Weka. There's a lot more to it, but I'm just going to show you the first button. So it's a powerful tool. So the first thing we do with the Weka Explorer is we're going to pre-process the file. We're going to choose it. Oop, I chose the wrong button. Open file. Now you get to see my messy workspace here. Workspace, Clojure land, down here somewhere, SpeechX classifier. It's in my resources. Oh, here it is. Okay, so you see that the data kind of pops up with this graph, and you get to choice of which features you want to choose. I'm just going to choose all of them. And then we're going to move to the Classify tab. And if you were really interested in doing this correctly, you would actually have your data split up into your data that you train on and your data that you test on. But I'm not that bothered. So I'm just going to use a whole set. I don't have a separate testing set, and I'm going to use this cross-validation, which is going to like cross-validate data against stuff that it's already seen to test it. So here's a classifier that it just immediately comes up as a default. It's called 0R. Let's just see what it works like on our data. It's pretty fast. Comes back, it correctly classified 41% of the instances. That really sucks. So let's choose another, shall we? How about some like Bayes stuff? How about like a naive Bayes? Let's see how that would work. 81% this time. So yeah, we're doing pretty well, but I think we can do even better. So let's go down here to some trees. Random forest. And let's see what we can get here. 85%, which I think is, I was pretty happy with it. I was like 85% for what I'm trying to do is good enough. And you can see here the confusion matrix. It's pretty certain about expressives, but it gets really kind of mixed up when it does get confused between the assertions and the questions. That's where it really has some trouble. So conclusion, random forest is the bomb. So it's a really good algorithm if you don't really know what you want to do, I would say just try that one. So great, we have a model that we want to use. How do we bring that into our code and use it then? Well, Clojure and Java interop, again, for the win. I'm just going to kind of show you a little bit about how we ported in the library. So of course, I'm going to pull in the Weka jar into my project file, and I'm going to create a new random forest model as a classifier. I have a function here that's going to get our data source, which is that ARFF file, and it's just going to convert it into, you know, the format that Weka is expecting. And then I have a function that's going to train the classifier. It's kind of hard to see here, but it's basically doing the same exact thing as the GUI was doing. It's using cross-validation, and then at the end it prints out the evaluator and the data that it was trained on. So that's really cool, but what about when we actually, if somebody's typing something in, we want to be able to classify that new thing that they put in, right? That wasn't in the ARFF file. So how do we go about doing that? Well, it's not actually really elegant, but basically you're just going to make it looks like a line of that ARFF file in that object, the constructed object, and you're just going to feed it in to Weka. So you're going to generate an instance of that data set, and then you're just going to say in this position here, I want a missing value that you're going to fill in for me. And then once we have that, then we can do some prediction. So we can predict the value, and it's going to spit out a 0 if it's a statement, a 1 if it's a question, and a 2 if it's an expressive. And then we're just going to transform that into keywords to make it a little bit easier for us to read and work with. So statement, question, or expressive. So here we go. In the results, we're going to train the classifier. We're going to get a predictor from it. We also get the data from that results, and we're going to turn around and use that in a predict function to be able to predict something new. So in this case, I'm passing in, I don't know if you remember the features, but like sentence length was one of them, and the number of nouns. So I'm passing in all ones there, and it says that it's an expressive, which is, you know, all my expressives are really short, so that totally makes sense. So again, let's step back and see where we are. I think we're almost there in our mini chatbot adventure. We have an ARFF file with data features. We can programmatically train a classifier. We can get in new text and transform that into features, and then we can turn that into a way to predict classification on new data. So here's a putting the whole thing together, classify text. We're taking in some new text. We parse that out into some stats, and then we turn that into features, and then we finally predict what our answer should be. So here's an example of our function, classify text. I like cheese. Turns out it's a statement. Classify text, how do you make cheese without the punctuation mark, is a question. And if we say something like right on, it's an expressive. So yeah, so we just need to kind of wrap this just in a proto chatbot that'll respond. And I am cheating just a little tiny bit here, right? So I'm going to make this function to respond to your text. If you do put a question mark in, I'm going to use it. So if you do put a question mark in, I'm going to return back that as a question. But otherwise, I'm going to classify that text and try to figure out what you wanted. And if I find out this question, I'm just going to say, that's an interesting question. And if it's a statement, I'm going to say nice to know. And it's expressive, I'm just going to do a smiley face. And this works at parties too, right? So here is a demo of it. Oops. You get here. Actually, I'm going to I'm going to start it up for, I'll start from the beginning so you can just see how long it takes here. Okay, so it loads up, and you can see that it's doing all the loading up the Stanford Cornell NLP. It's getting like the POS taggers, and then it's loading the classifiers, and then it's actually running the data for the classifier like right there. So correctly classified instances 85% of the time. So hello, let's chat. All right, who's got something for me to put in here? What is your favorite color? That's an interesting question. Yay! Okay.
Well, if you concatenate it, the what is, we'll handle that already.
What do you mean, like what's?
Just like what.
Oh, like what is?
What, or like, what's your favorite color?
Like this? What's?
Yeah.
What's your? Oh, I said what is you favorite color? See, I can't even type anyway.
You got it right.
Okay.
Bring me a shrubbery.
Bring me a shrubbery. Oh, so sad. Shrubberies are very nice decorations. Oh man. DevFest is a great conference. Oh man. Did I do something wrong? Oh no. That was just really inaccurate.
You only have about 400 data points, so.
Okay.
That is an
That is an
interesting question.
interesting question. All right. Woo. Any more? Come on. Would you like to play a game? Oh, so it's not all that. What about an expressive?
You rock.
Ooh, you rock. All right, so I got that one. What, YOLO? YOLO. So yeah, as somebody pointed out, like there's only like a really small amount of data. If we actually want to do something useful, we need machine learning. We need to do it like much more. But this is definitely, kind of fun. Any more? Want to try? No? Okay. Back to the presentation.
So what does the random forest do? What does that look like?
Oh, the random forest algorithm itself, it's a decision tree that's more complicated than just your regular decision tree. The actual algorithm itself, I think, is copyrighted, but they've got I think Google has an open source implementation of it that you can use, if I'm not mistaken. Right. Yeah, so just stepping back and looking at what we've done here. So on our journey, first you have to get your data set together, your corpus, and we got that together with statements, questions, and expressives. And anybody working in data science that I've talked to or doing machine learning, you spend most of your time getting data together and cleaning it up. That's, that's from what I've heard of experiences. Then we parsed and annotated that with the Stanford Core NLP library and got information that we could then use for features. We looked at an academic paper to stand on the shoulders of giants to choose which features to use, and we used those to generate our ARFF files. We used Weka to try out different classifiers and see which one was more appropriate to our data set. And then once we've chosen one, then we could tie that in programmatically into our program and use it to train and predict things in a programmatic way. And finally, we tied it all together with code and a REPL and some very proto responses so we could play with it. So in the end, I think that humans are pretty cool still. And if you are interested in playing with any of this code, it's out there. Like I said, it's nothing for production at all. It's all experimentation, but it's out there if you want to look at it. There's Stanford Talk to get the POS taggings. There's speech act classifiers. And this is interesting. I had blogged about this, and some fellow that actually really knows how to do machine learning and NLP stuff took my little baby corpus and made an example out of it. And he's got an actually full-featured thing that if you're interested in using this, you might want to use it, and you can play with this data set in particular. So yeah, so that's all I have here, but I'd be happy to answer any questions, understanding that someone, I might not know what I'm talking about. Yes?
I was going to say, from what you understand, does the order of the words impact whether it thinks it's a question or a statement? Do you think like, winter is coming versus is winter coming? It's the same words, but the order.
Let's try it out, right? Okay, winter is coming. Is winter coming? So I think in that case, it's probably looking at the sentence length. I think probably the way I did my expressives, I had them all short, so it's probably dominating anything. Pardon? There was positional? No, there was nothing positional. There was like number of nouns. Yeah, yeah, yeah. That's true. That's true. Yeah.
You mentioned there's a bunch of different algorithms and you can pick one.
Mm-hmm.
I believe I've read somewhere that sometimes like having a bunch of algorithms vote is like a way to improve things. Is there a way to do that you could think of with the Weka stuff? Would it be possible to build like a consensus? Like a voting system?
So I have no idea. So if
Notice up there, one of the lines is relative square error.
oh, here, pretend.
So that's really talking about the residual sum of squares, and the idea is that if you basically you could choose whatever algorithm you want to do. Just like you're saying, if you were to take multiple different algorithms and run them against the different data sets,
Mhm.
the lower the residual sum of squares is, and the higher the correctly classified instances are, the better results you're going to get. So the other thing that she kind of mentioned it earlier, but she didn't really go into depth about it, is that if you take so right now she ran everything against the training set,
Mm-hmm.
but if you split it 2 more times, one end to validate, you're not because you, one end to the validation and one end to the test, and the training, if you run it against that, you're going to get some result out of that, right? You're going to get some kind of residual sum of squares. But then if you take that and apply it against the validation set, and then again against the testing set, you're going to get better and better and better against, the results are going to come out better. And the reason that you do that is if you run it just against the training, essentially you're biased towards the data that you've got in front of you. Yeah, so you use the test set to validate against essentially stuff that your algorithm doesn't really know about. If that makes sense.
Yeah, yeah, no, it does. Yeah. The thing that I found interesting, like I said, I kind of went into this little project knowing nothing about the whole field, and just I was amazed of how deep I got fast, right? Of just trying to do anything with natural language. It's just, whoa. You know, you start pulling on a thread, and all of a sudden you're
There's some
down
really
there.
great courses on like Coursera.
Mhm.
And, I think Once Udacity has a couple too. But I'm taking the Coursera stuff right now, and
Oh.
it's fascinating.
Yeah.
So you get to see like the inner workings of all the algorithms. That
Oh,
come out
cool.
now.
Very cool.
Yeah.
Very cool. Anybody else have any questions or anything to add? No? Okay. Well, great. Well, thank you for letting me talk.